Good morning, everyone, and welcome to SIBGRAPI 2021 first technical session on graphics and visualization. I am Manuel Oliveira from the Federal University of Rio Grande do Sul, and will be chairing the session, which has 6 excellent papers covering a variety of subjects ranging from visualization techniques, computational geometry, fluid simulation, shadow mapping, and deep learning solutions applied to mixed reality and computer-aided design applications. So this is how we're going to proceed. For each work, we will start by playing a 5-minute summary of the paper, which will be followed by a question and answer session. So I would like then to encourage you to submit questions to the authors through the YouTube chat as well as through the Discord channel for this session. So the first paper of the session is entitled A New Focus plus Context Visualization Technique for Inspecting Black Oil Reservoir Models. The authors are Luiz Felipe Neto and Valdemar Celis, both from TechGraphi, PUC-Rio. We can now play the video.
Hi! In this work, we propose a new Focus plus context visualization technique for the inspection of simulated black oil reservoir models. Simulated reservoir models are used in the oil and gas industry to predict and plan the exploration of petroleum fields. Reservoir engineers try different well arrangements and exploration strategies to maximize the economic return of the reservoir. We are interested in helping experts to better understand the physical phenomena around injector and producer wells. For this reason, we propose the following cutaway visualization, where users can select one or more wells as objects of interest to apply the cutaway. A well here is represented by cylinders that follows the well trajectory. Our cutaway has two visualization modes, a view-dependent mode where the cutting surface can be updated by controlling the cut aperture or by changing the camera position, and a view-independent mode that, when activated, freezes the cutaway surface generation, and we can change the camera position without modifying the cutting surface. This provides us with motion parallax, which helps to infer the depth of the well in the reservoir cutaway. In both modes, we can enable the wireframe for the reservoir external faces and for the cutting surface geological layers. In the view-dependent mode, we can change the selected wells to apply the cutaway. In our view-dependent cutaway, we represent our cutting surface by a depth map and an intersection map with the dimensions of the frame buffer. The depth map is obtained by using the backface depth of the selected wells as input to compute a distance transform with the jump flooding algorithm. The intersection map represents positions of the cutting surface depth map that are inside the reservoir cells. This is computed with an efficient point location algorithm in GPU. We render our model applying the cutaway by comparing z-values from the depth map with the reservoir model hull fragments depth. If the model fragments are between the camera and depth map, we check if an intersection has occurred and use the assigned color if it does. Otherwise, we discard the fragments. Model fragments that are not between the camera and the cutting surface depth map are drawn as they are. After rendering the reservoir cutaway, we can draw the select wells to complete our visualization. During the view-dependent cutaway visualization, we can enable the view-independent mode. We want to change the camera position to better inspect the cutaway, but we don't want to change its shape with the camera in motion. Thus, in the view-independent mode, the depth map and intersection map are no longer updated, and we use the ones set in the last draw. Then, we render the cutaway cutting surface with the relief mapping algorithm, using intersection map to assign the colors to the cutting surface. Please check our papers for more details. We also propose the box-shaped cutaway. This kind of cutaway shape is important because it maintains the natural alignment of geological models. We are still using a depth-based cutting surface, but we have built this one with an aligned bounding box of the select wells. After applying the cutaway to the reservoir model, we also draw the reservoir bottom layer immediately below the selected well. Despite our initial goal to present a visualization technique to inspect the vicinity of wells, we ended up with a more general visualization. We can compute the cutting surface for other objects of interest. For example, here we used a set of cells as object of interest. We evaluate the performance of our visualization with 5 reservoir models, with cell counting ranging from 30,000 cells to 16 million cells, as can be seen in Table 1. Our cutaway algorithm shows a good performance even for a large model with 16 million cells. We also evaluate the performance of each phase of the view-dependent cone-shaped cutaway, with increasing size for the cutting surface, as seen in Table 3. As the cut size increases, we observe that the intersection map is responsible for the majority increase in the cost of the visualization. To conclude, we have the following contributions. We have built a new visualization to inspect black oil reservoir simulation results, a new efficient algorithm to handle cone-shaped cutting surface based on a point location procedure, capable of handling objects of interest of any shape, a new box-shaped cutting surface construction algorithm using a reservoir layer as the bottom wall, and an efficient view-independent cutting surface construction based on the relief mapping algorithm. Thank you for your time.
Okay, thanks, Luis, for the presentation. While we wait for questions from the audience, let me get started by asking you, you proposed two cutaway strategies, one based on cone shape and another one which is based on a box-shaped structure, right? So the question for you would be, when should a user select either the, say, the cone shape versus the box shaped cut away element?
Okay, good morning, everyone. Good morning, everyone, and thank you for the question, Professor Manuel. I think the best way to reason about this is we are going to use the box-shaped cutaway when we want to have a more infer more precisely the depth of the well trajectory inside the reservoir, because this box-shaped cutaway, as I said in the video, it maintains the natural alignment of the model. So yeah, and we are used to see box-shaped things like our house every day, and our perceptual or how we think about shapes is more aligned with this kind of a box-shaped cut. So if you want to have a more precise feedback from the depth of the well trajectory inside the reservoir, the box-shaped one would be the answer for it. But in the cone-shaped cutaway, we still can see the scalar field map more closely to the well trajectory, because it will be more coupled with the well format, right? Since it's a distance transform, it maintains this appearance of the well.
Okay, thanks. Question from Joaquim Bento. What happens with the elements around the cut? Is the compatibility an issue?
Okay, so we choose what objects we want to cut, and when we are applying the cutaway, we are choosing to cut only reservoir cells. If you have other objects, let's say you can have wells that are not defined as objects of interest, and they are not going to be cut because they are going to be drawn in a later pass, and this is would not be an issue. I don't understand exactly what's the compatibility question.
Okay. And so have you tried the proposed technique, the proposed visualization technique on head-mounted displays so that you could, say, inspect the and explore the wells and the geological structures, close by?
Well, to have a head-mounted display at home to try new visualization things is something that I wish, but I don't have at the moment. And it's sure interesting research question, and I want to maybe someday answer it, but not now. I can't answer now because I haven't tried it.
But how do you think the sort of a user would react to this? I mean, based on your experience working on the oil and gas industry,
I think
do you
it
think
would
it's
be
something
really.
they would be interested uh, in trying?
I think when we when I think about head-mounted displays and visualization, I think in not just one person using it, but like three or more persons sharing the same visualization. So they are seeing the same reservoir model, and they are cutting and discussing about it. It's that kind of thing that we see in promotional videos about architecture and etc. And I think it would be really interesting to see it in action with reservoir models.
Okay, thanks. So Beatriz Andrade says, very interesting work. Congratulations. How do you consider the different kinds of soil in the cuts?
So the reservoir model has scalar field properties mapped to it, and we can we can see one property at a time. For example, we have show images with the video with pressure and the others with um, um, oil saturation or water saturation. So you have this single kind of property. But let's suppose in a more complex tool, you would select based on a kind of water property that maybe is related to the soil um, per se. And this could be helped to select what we want to cut. For example, using cells as objects of interest. That's something that we can do also, and that would be the answer to it. But I don't make this kind of uh, um, hypothesis now about the kind of soil that you are going to cut.
Okay, thank you. Selma Guimarães da Silva says, nice presentation. Is your tool available for download?
No, it's not.
Okay. Um, so I think we are up to 5 minutes already. So we can continue this discussion through Discord. So I encourage you to continue sending questions to Luis Felipe through Discord. And now we're going to move on for the next presentation. The second paper in the session is entitled Optimized 2D Ball Trees by Luiz Retondaro and Cláudio Esperança. Luiz is from Centro Federal de Educação Tecnológica do Rio de Janeiro, and Cláudio Esperança from the Federal University of Rio de Janeiro.
Binary ball trees are hierarchical bound structures where each node consists of a ball enclosing its children. Approaches for building an optimal ball tree for a given set of leaves typically rely on minimizing some function of the shape of the tree, regardless of the intended application. In this paper, we examined the problem of building ball trees for 2D primitives, trying to balance construction time with the efficiency of the produced trees with respect to a set of distance-based queries. In particular, we present three new construction algorithms, propose an optimization whereby each internal node is the smallest ball enclosing all leaves rooted at that node, and describe enhancement to several distance query algorithms. Moreover, an extensive experimental study was conducted in order to evaluate our algorithms with different kinds of datasets, including ball collections that approximate 2D shapes.
So let's move on to the questions, please.
You just played the short video rather than the full length video.
Okay, yes, that was the plan. So the paper proposes three different algorithms for constructing, the 2D ball trees. So do you have any guidelines for the users in terms of what kinds of queries or applications each one of those three variations are most appropriated for?
Well, we have quite a range of ball tree construction algorithms. Some of them uh, were proposed originally a long time ago by this very famous person now, Omohundro. And the thing is, the best performing algorithm is really slow. So we try to figure out ways of doing sort of close to the same things, to the same performance, but with a faster algorithm. And I think we have managed to do that. I mean, the performance is something that you can tune with the algorithms we presented in this paper. But I mean, the application is actually depending on what you're trying to do. Ball trees are very good for intersection queries, so and distance queries. And the fact that ball trees give you a very interesting level of detail view of any kind of object is very advantageous for many applications. The application we're trying to build here, and this was the motivation for this work, was segmenting and rearranging documents, parts of documents. So the idea is that we have all of these documents that are segmented into blobs of text and pictures. And each of them is going to be represented by a ball tree, so we can rearrange them and do collision detection between the various kinds of shapes. And ball trees are very, very good for that. And they are nicer to work with regular collision detection techniques, which are sort of messy in 2D. And ball trees, especially if you have to do things like we're planning to do, like mixing together parts of segments of the image into one big segment and then partitioning this into small parts, ball trees are very good for that.
Yeah, but since you propose three different variations, I mean Q, V0, and V1, I mean, is Q more appropriate for a particular kind of query or detecting collision compared to V0 or V1? Or so how would you recommend the use?
Q is very good in the sense that you can tune Q to give you better performance or better approximation. And this is not the case with the other algorithms. Q is by tuning one particular parameter, you can make it run faster with lower fidelity or run slower with higher fidelity. So this, I think Q is a very nice algorithm for this reason. In certain applications, you need to build the tree really quick. And in other applications, you need to build a very high fidelity ball tree. And but this, I mean, by tuning this parameter, you can either get one or the other. So can you just use Q and tune it to your particular application, and you should be fine.
And it seems that all the proposed algorithms would have a direct extension to 3D, right?
Yeah.
So, and it seems that Q would still be extended and keep the same asymptotic quadratic cost.
Yeah.
The
That
other
remains to
two,
be seen. We haven't tried that yet.
yeah, all right, because the other ones require computing Voronoi diagrams, and those
Right.
would increase the cost with dimensionality. So, but
Right.
the first one,
That's
it seems that you could make it 3D with
Yeah.
the same cost. But so let me then in the have you considered, for instance, using instead of computing the precise Voronoi diagram, use some approximate solution for Voronoi diagrams? What would be the impact of this on, say, the cost and the accuracy of the results?
I mean, there are many things that can do with Voronoi diagrams. We have actually tried quite a few variations that is put in the paper, but in the nutshell, Voronoi is good, but not as good as we thought it would be. So Voronoi is nice because it gives you a very high level view of the distribution, the overall spatial distribution. But as you start to process and have to rebuild the Voronoi diagram over and over again, it gets less efficient. So I suspect this is the same reason why Omohundro didn't propose any Voronoi diagram-based ball tree construction algorithm, because it looks like a very good idea and it works very fine in certain cases, but it's not as bulletproof as the other algorithms.
Okay, so a last quick question here. From at the moment, no questions from the audience. So all the proposed algorithms have a cost that is at least quadratic.
Right.
So how do you expect, or have you thought about possible solutions that could allow this to be used in this three-dimensional environment? If you'd like to extend this, how would you do it?
Well, if you want a very quick algorithm, the one based on KD trees is very quick. And in 3D, it all depends on what kind of application you try to do. And quadratic is not so bad for a reasonable amount of balls. But if you have a really huge amount of balls to work with, then there's no way around it if you want to have high fidelity. And also you need quadratic at the minimum if you want to do the enclosed leaves optimization, because just to do the optimization is quadratic. So anything, even if you construct the ball tree quicker, you'll have to spend quadratic time just to come up with all leaves enclosing optimization, because this is also quadratic.
Thank you very much. Now I have to move on to the next paper.
Okay.
Thanks again.
Thank you. Bye. See you all.
So the third paper in the session is entitled "A Particle in Cell Method for Anisotropic Fluid Simulation." The authors are Emanuel Parreiras, Marcelo Bernardes Vieira, Arthur Machado, Marcelo Reni. These are from Universidade Federal de Juiz de Fora, and Gilson Girardi from Laboratório Nacional de Computação Científica. Let's see the video then.
Hi, welcome to our presentation. I will talk about the paper A Particle in Cell Method for Anisotropic Fluid Simulation. I'm Emanuel Antônio Parreiras, a master student at the Universidade Federal de Juiz de Fora and the announcer of this video. Controlling the fluid path inside a scene is extremely important to enable the artist to create many types of effects and unimaginable scenes. The most common technique is to build a force field to modulate the fluid flow. In this work, we propose a new numerical tool for flow control using simulation in an isotropic medium. To execute these simulations, a modification of Navier-Stokes equations is needed. In this case, the tensor field acts as a medium property of the fluid domain. It's important to say that to solve these equations, the tensor field needs to respect two restrictions. First, it needs to be symmetric positive definite, and second, the tensor field does not vary over time. In this paper, we focus on simulating liquids, which led us to build our method based on flip. Using the classic flip approach, we propose a modification to the projection and advection modulus. One contribution of this paper is the definition of new boundary conditions. In this figure, the fluid empty boundary is highlighted in red. Its face has a velocity u. In ordinary interaction, this velocity would not be affected, but the tensor's action modulates the fluid velocity on the boundary. Therefore, a part of it will be reflected. The difference between the actual velocity and that reflected by the tensor is defined as the boundary velocity. This difference changes the divergence at the boundary surface. Therefore, the Neumann and Dirichlet conditions were extrapolated to this case. Another contribution of this paper is the adaptation of the Ronchi-Coulter integrator to also integrate the tensor along the particle's trajectory. In the classical advection, it is made only with the velocity field. In our case, we use the method of characteristics to incorporate the use of tensors into the third-order Ronchi-Coulter method, which in each step is added an acceleration component coming from T minus U equation. The anisotropic projection is obtained from the solution of the Poisson equation. Another contribution of our work is a new discretization for the left side of the equation. We start with a macrogrid curve and compute a cell-centered gradient field. From this field, we apply a t-gradient operator, which is defined by multiplying a tensor field t by a gradient field. To compute the Laplacian of curve, we calculate the divergence for the reference cell using, in the case, the four neighboring cells. You can note the generated linear system is undetermined. To work around this, we use a linear interpolation. The linear system obtained from this mask is not symmetric, so we use the biconjugate gradient stabilizing method to solve it. Note that for an isotropic tensor, our method is reduced to the classical approach with -6 in the mask center. If we use a tensor with lambda1 equals lambda2 equals 1, lambda3 equals 0.1, and the eigenvectors align with the canonical axis, we can observe a variation corresponding to lambda3 and the vertical eigenvector. The cloth experiment shows us the applicability in simulating some permeable materials, and the modeling was made using parametric paraboloid as a planar tensor layer. In this video, we can observe how the eigenvalue parameter influences the simulation and changes the behavior of the material that we can simulate. The method we propose is able to perform fluid transport in an isotropic medium and generate smooth simulations. In future works, we will focus on improving the Poisson discretization, aiming to obtain a linear system well conditioned, even in high anisotropic fields. Thereby, we can obtain better control in these cases.
Okay, so let's go to the question and answer session. So thanks, Manuel, for the presentation.
Thanks for all.
The technique uses a Mac grid. And the very first question that I would like to ask you is, do you think it would be possible to adapt the proposed technique to be used with curvilinear grids?
Yeah, yes, I can. I can think it's possible.
So how would you do it? Any thoughts on that?
No.
Okay. So let's see. Usually, in the entertainment industry, people use the fluid simulations with artistic control. So
Yeah,
oftentimes, an artist, use some hand, control device to define trajectories for fluids and so.
yeah,
Do you think it would be possible, for instance, to create some sort of interface and use this to feed and define the tensors that you need in your technique in order to animate those flows?
yeah. It is possible, and is an open area. Create tensor fields is not easy, and some high anisotropic fields can be very difficult, not even to solve, but to design to. But um, we demonstrate in the paper that we can use the tensor field to control the fluid path, and is an open area. And the future works we use.
Okay. So, question from Joaquim Bento. Um, is the grid uniform? Can you refine the grid in some areas? I mean, can you
Yes,
adapt the grid according to your needs?
yes. Uh, our method is separated into fluid areas. We can define a linear system into small pieces of fluid uh, that is, that in the fluid domain.
So, but the question, I think, the first question is the grid uniform? It has to be uniform because as you then do the refinement in some areas, you do this adaptive adjustments. Then I would probably guess that it would not be uniform anymore. So,
Yeah,
is it uniform or it does not need to be?
our method treats as a uniform grid, but
Okay.
the flip method in some cases can be not uniform. So I I I believe that's possible too.
Okay, thanks. So, question from Afonso Paiva. Could you talk about the accuracy order in the Poisson pressure solver?
Is the accuracy um, ha- um, is the same the traditional isotropic mask.
All right, okay. Um, so, thank you very much, Emmanuel, for the answers. We should then move to the next presentation. The next paper is entitled Non-Overlapping Geometric Shadow Map. The authors are Edson Mesquita, Creto Vidal, Joaquim Bento Cavalcante Neto, and Rafael Ivo. They are all from Universidade Federal do Ceará. And Edison should be with us answering questions. So let's play the video.
Hi, my name is Edison Miller, and I'm here to present the paper entitled Non-Overlapping Geometric Shadow Map. The co-authors of this work are Creto Augusto Vidal, Joaquim Bento Cavalcante Neto, and Rafael Fernandes Ivo. We all are from the Federal University of Ceará, Brazil. Shadows play a crucial role in conferring realism to a scene, since they provide the necessary clues that enable three-dimensional perception of virtual models, and reveal hidden geometries of the scene from some viewpoints. However, hard shadows are still an important and challenging problem, especially in large-scale open-world games, since high quality must be achieved in real time and with low memory consumption. We propose a pre-computed geometric shadow technique called non-overlapping geometric shadow map that enables the construction of high-quality hard shadows from static lights for any point of view. Our solution also generates shadows with better quality than standard shadow mapping techniques, while maintaining real-time performance and using a smaller memory footprint than compression techniques. The construction of Node.js occurs in a pre-processing phase that consists of three steps. The first step is projecting the scene into the viewplane of a camera that is placed at the light position, and points in the same direction as the main direction of the light. The backface triangles are then removed. An OTM is constructed to remove the need for storing and checking regions that are not visible from the light. This is done by removing the hidden surfaces. Each polygon is clipped by the ones that are closer to the light. The resulting geometry is then triangulated to increase GPU compatibility. The depth range multigrid is constructed by first labeling the NOTM triangles with an ID. An OTM is then recursively divided into k by k grids, and each grid stores the IDs of the triangles within its region. The subdivision continues recursively until a limit level of recursion is reached, or the number of tags in the cells list is smaller than a threshold t given by the grid division limit equation. Then, the local tag lists are merged to reduce memory consumption. This is done by ordering the cells by tag list size. Then, they are inserted into the global list. In the global list, each cell keeps a pointer to the start position and size of its list. DRMG is then vectorized to increase compatibility and performance in GPUs. The DMRG final structure is composed of cells of h byte. Each cell has a minimum and maximum depth, the starting position of the next structure, and the size of the leaf list. A size lower than 0 indicates that the next structure is a multigrid. Here is a visualization of the DRMG limitation boxes. The rendering process is similar to the one of the standard shadow mapping techniques. The scene is projected into the viewer position, then each fragment f is tested to see whether it is in shadow. This is done by projecting f into the light's camera and checking in which cell f falls. If it's a subdivided cell, the pointer structure assigns the projected point to the correct subdivision level. If it is a leaf, the pointer to the cell's NOTM is used to verify whether or not the point is occluded. These four scenes were used to test our technique. In the majority of the cases, the amount of triangles is reduced after the removal of hidden surfaces. Here we can see the advantages of the Node.js. The first column shows the number of triangles inside each fragment. In the second column, the blue color indicates the regions that fail the depth range test. The third column shows the number of tests per fragment using the fact that the triangles are disjoint. This allows the shadow check to stop when the first occluder is found. These figures show the impact in leaf depth when using different grids resolution. And here we can see the comparison of four results with shadow map compression techniques. Our method runs faster and uses less memory. This concludes the presentation. Thank you for watching.
So thanks, Edison. Very interesting technique, very different. I mean, using geometry. So since you use geometry in order to make your shadow test, a natural question that comes up to mind is how does the technique scales with the number of light sources? Because then you have to create those you call canopy, now, right? Those proxy
Right.
geometry.
Good morning, everyone. As in the normal shadow map technique, for each camera, we need to have a pre-computed buffer that shows the depth of each element. In our case, for each light source, we need to construct our canopy that is constructed in a pre-processing phase, and for each fragment in the rendering phase, we check against each canopy of each light.
Yeah, but in terms of memory, how does this scale? Because you say it's efficient and everything, but you need to somehow make copies of parts of the geometry of the entire scene that you have to render. So you have to keep those copies associated to one for each light source plus the complete scene description. So how much how much memory do you need in order to store all those canopies?
This depends on the geometry that we are using in the scene. Large scenes with complex geometries need more memory to be stored, and also depends on the view position of the light. If a light is looking at a place with a high amount of memories that will be put in the canopy, the amount of memory need will be higher. However, as we show in our results, we use less memory per pre-computed shadow map than other techniques that use are pre-computed and use compression, because we are not using pixels or voxels. We are using the real geometry, and we are not using as much geometry as the original scene, since you are cutting a majority of the scene that is not visible from the light.
Okay, thanks. So Lorena Souza says, "Great job, Edson." Uh, could you explain why the grid division equation?
The, or grid, he stops dividing if he gets into a depth that is preset by the user, or he reaches the grid division limit equation that is set to the higher we get in the depth, the higher the amount of triangles that you can store in a grid. This is done because higher depth means that each leaf has a smaller area. So if the area is smaller, it reduces the chance of we getting at the leaf, so we can store more triangles there, and this won't impact so much the performance.
So in the scenario of rendering scenes, we often use sort of smooth shadows, right? And so do you if the scenario use some sort of light attenuation, you probably would not need to consider the entire range or depth range of the scene in order to compute your canopy. You could probably stop earlier because light would have attenuated so much that would not project shadows. Do you take this into consideration? Do you use a specified or pre-specified depth range to construct your canopy, or do you have to use the entire scene to do it?
Well, we pre-computed the entire scene into the canopy because we want this to be used in every place that we put our camera. Every place the viewer is, we have already pre-computed the shadow for that region. But we
But
can, but you can choose just the region of the scene to be rendered into the canopy.
yeah, but say maybe you might be too far from the light source, and then if there is some light attenuation going on, there should not be this very hard shadow
Hard shadow.
very far from the light source. How do you handle the situation?
Yeah. Now we are only working with hard shadows, but we are working in future works to add something like soft shadows and the light attenuation. But now we only work with hard shadows.
Okay, so this leads to my next question. So how would you implement soft shadows?
Oh, this is a hard question, and we are thinking of things like interpolation of multi canopies that are in points of the area light source, and this interpolation of this multi-point source, or just a linear interpolation between paths of the camera.
Okay, so yeah, I was thinking about this, and it occurred to me that you may, for instance, when you're checking the occlusion against the canopy, your proxy geometry, right? You could consider how close you are from the border of this proxy geometry, right? And say if you consider maybe a Gaussian kernel, then you could consider how much of it is inside this geometry, how much goes beyond the border, and use this area, right? Uh, this relative area to decide how much you should attenuate the the shadow there in terms of doing this pretty much like uh, 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 this pre-filtering strategies that you can apply. I forgot the acronym now, but um, anyway, in shadow mapping, you can use multiple neighbor cells and then average their contributions. So what uh, PCF, I guess, percentage closest filtering, yes, PCF. And then you take the average of the elements that are lit and the ones are in shadow, and then you estimate a value for your soft shadow. So you might consider this analog for 3D and saying checking how close from the border of the proxy geometry you are, and then you could probably arrive at some interesting solution. It's just a suggestion. So but thank you very much
It's a good approach. Thank you.
for your answers. We should then move on to the next paper. So the next paper is entitled Spatially and Color Consistent Environment Lighting Estimation Using Deep Neural Networks for Mixed Reality. The authors are Bruno Marx, Esteban Plua, Anselmo Montenegro, and Cristina Vasconcelos. Bruno Marx is from Universidade Federal do ABC, and Esteban, Anselmo, Cristina, and Cristina are from Universidade Federal Fluminense. We can play the video.
Hello, my name is Bruno Marx, and this is an overview of our work, especially in color consistent environment light estimation using deep neural networks for mixed reality. We talked about how to bring high quality lighting to real-time mixed reality with the use of deep learning. So here we have two examples of mixed reality. The context of this work is the lighting in mixed reality applications, where we blend virtual rendered content with real-world images. Here we have an example of inconsistent lighting and how it can impact the mixed reality applications. Despite being in a very different environment, light conditions, the three frames here show the main virtual character rendered using the same lighting. In all the frames, the main source of lighting for the virtual object seems to be above the character head, so it's obviously wrong position. So our main objective here is to produce a light estimation that allows the introduction of virtual objects in real-world scenario, producing pleasant visuals, such as these examples here. This is our method estimation model. It takes as input an RGB image. This image represents an aerial field of view of the environment, such as the images acquired through the camera and the mixed reality glasses. The RGB image is fed to a convolutional neural network that extracts features, producing the latent feature vectors of our problem. We fed the result latent features to a spherical harmonic light decoder and a LUV color space decoder. The main idea here of this model is to multitask the light estimation and the color space mapping to obtain a color constant light estimation. For training our model, we produce an appropriate dataset through our mixed reality framework. Our approach consists of using real-world HDR panoramas to produce mixed reality views, where a mixed reality view consists of a pair, the environment image and the spherical harmonics lighting. We first produce the image of the environment using a cropped projection of the panorama, as you see in B. This image is then converted to a low dynamic range image, and we continue the process in C, where we take the original HDR panorama and produce a warped panorama that represents the lighting in this position. So we take our spherical harmonics functions and project these functions in the warped panorama to produce the spherical harmonics lighting. The architecture we use is a shuffle net for the main features extractor. We use a custom architecture for LUV decoder and IMLP for the spherical harmonics encoder. Here we have some comparisons between our results and the state of the art. As you can see, in the first column we have the ground truth lighting. In the second column we have our method estimations. And on the third column we have Garons et al. And on the fourth column we have Gardner et al. Comparing our method with Garons, in the third column, our method produces a more constant lighting estimation regarding the color and the direction, producing a pleasing visual. While comparing it with Gardner et al. Work in the fourth column, they estimate a higher intensity environment lighting for almost all cases and does not appear to blend naturally with the environment. Here we have an example of spatially variant lighting. This means that we move our model in different places across the scene, and the estimated light should reflect these changes in the position. Our method reacts to this change, producing plausible lighting scenarios. It also interacts with local environments by mimicking some global illumination effects, such as the diffuse color of the surroundings and other effects that's not possible with other methods. And one more example here, where the bunny reacts to the window on the right side of the video, showing the spatially variant lighting effects. Thank you very much. I'm now happy to answer any questions about our work.
Okay, thanks, Bruno. I would like to start while we wait for questions from the audience. I would like to start with a clarification, because in the paper, you said that you train a CNN. In order to train the CNN, you warp an HDR panorama to simulate a camera path, right?
Yeah.
Could you please explain how do you warp this panorama? It was not clear to me.
Hello, good morning, everyone. Thank you for the question. This warp operation, we're trying to simulate the camera movement in the environment. We don't have a method to perform this operation without the geometry of the scene. So we do a little estimation of this warp operation. Actually, we warp the environment map of the scene in our sphere, and we try to translate the camera, the focus of the camera, first rotating the panorama with the right orientation, and then we try to warp this position by moving the camera in the z-axis. It's a little hard to explain with just words like this, but the main idea is to warp the panorama in a sphere. So every point of the environment, it's approximated in the same distance from the center of this sphere. So this is the approximation. We don't have a method to exactly move the camera and work the panorama exactly. So this is a little approximation we do on our method, but it's worked quite well in our case.
Okay.
In the paper, we have some reference for this warp operation. I think it could be more clear
Okay.
to understand.
So we have a question from Edson Mesquita. How does the technique work with black and white regions? And he also asks, have you used the HDRs with flash on and off?
How it's work with white and black. Well, actually, since we are working with HDR panoramas, we don't have so much problem with some black, very black or very white portion of the scene. For example, in the camera here where I am presenting, here we have some clamping on the bright side because this is a SDR image, right? In HDR, we have a high range of values, so we don't lost information in the bright area. So this is our ground truth, and this is the information that we use to train our network. So this is actually a contribution of our work. It's learn how to represent lighting from SDR content, that's the image of the camera, and estimate a high dynamic range image. And the second part of the question was about.
Have you used the HDRs with the flash on and off? Again, maybe.
Well, actually, no. We use only the natural illumination of the scene.
Okay. So one thing that I'm curious about is the fact that you're using a spherical harmonics representation for the light environment, and this would require you to have this spherical panorama as you mentioned, but in a sort of augmented reality application, you have a camera and you show that you only have a small window of this entire spherical image. So you cannot, in that situation, recover the full lighting function for the environment, right? So this means that if you are doing this on the fly, maybe the camera is pointing in a direction and the only light that you're using to relight the object is what is visible by the camera. But maybe there is a window, as in your case, to the side. And it would probably not be taken into account. But then as you switch directions, maybe you rotate the camera a little bit, then the window shows up and the lighting changes completely. So how do you handle this? I mean, wouldn't this introduce some inconsistency in the lighting?
Well, actually, yes and no. Let me explain. First, yes, you are right. We are just constrained to a little narrow field of view of the scene. But the neural network, what it do actually, it hallucinates informations about the entire scene. So it tries to match the entire scene using only a narrow field of view. So if have in this example that you said we have the first picture that does not show the window, for example, but the network only based on this narrow field of view tries to hallucinate the whole field of view.
Okay.
But naturally, some inconsistency happens. You can see in the video sometimes there is some flickering that happens in the scene, the light estimation. But I think the results were quite good because they don't have whole information about the scene.
Okay. So, based on the last videos that you showed, it seems that you're using a diffuse precomputed radiance transfer kind of approach to do the illumination, right, of the
Yeah.
object, so diffuse object. And so a natural question is, can this technique handle multiple synthetic objects in the scene? And in this case, how would you say compute the transfer function among those multiple objects that might be, moving with respect to each other, so dynamic change in this function?
Well, actually, you can perform this the inference of the model into each object separately. So we have multiple objects. We can perform the inference in each object separately, right? But we don't have this interaction between the objects. So our method does not handle this kind of global illumination where each object interacts with each other. But we can make its work actually into multiple objects, but just with the lighting of the scene. But the objects does not contribute to the lighting of the scene. I don't know if it was clear.
Yeah. Okay. So, unfortunately, we are over time. We have more questions from the audience. So I encourage you to answer those questions through Discord, right? We have to move to the next paper of the session. So,
Thank
thank
you
you
very
very much,
much.
Bruno.
Thank you.
So the next and last paper of the session is entitled Deep Learning-Based Framework for Shape Instance Registration on 3D CAD Models. The authors are Lucas Figueiredo, Paulo Iveson, and Valdemar Celis. They are all from TechGraph PUC-Rio. You can play the video.
Hello, my name is Lucas and I'm going to present deep learning-based framework for shape instance registration on 3D CAD models. 3D CAD models are widely used in engineering projects, and the complexity grows by the year, posing challenges to efficient storage, transmission, and handling. Iveson and Celis remove the redundant information by identifying instances of similar meshes and computing an affine transformation between them, but their method depends on vertex ordering and surface triangulation. By removing this redundancy, we can reduce the model representation and improve handling. The question is, how to do that without depending on the mesh topology? Several techniques were proposed to perform shape-point cloud registration, but they are not well suited for the 3D CAD domain. Duerol in 2010 extended the ICP algorithm, obtaining an affine transformation for the point cloud registration. But, as we see in the further of the presentation, we are able to obtain better results with the proposed method. Inspired by the recent work, we developed a deep learning-based framework to remove redundant information of similar triangle meshes by relying on PointNet++ and obtaining an optimal affine transformation. By relying on point clouds, we are independent of vertex ordering and surface triangulation. We also guarantee an upper bound on any surface errors. The framework takes as input a triangle mesh, perform a preprocessing step, which composed by a normalization step, which the mesh is centralized in the origin and aligned with the 3D axis, and then a uniform point cloud sampler. The sampler point cloud is passed to the PointNet++ and obtains the base type, which is used to perform the instance registration. On the instance registration step, our goal is to obtain a matrix M which transforms a source mesh into a target mesh. To do so, we have two loops. The outer loop, we continuously update the point cloud's density and check if the upper bound was already achieved. And in the inner loop, we use the add optimizer alongside with the chamfer distance to continuously update M, stopping when the chamfer distance starts to decrease, avoiding loss of time in unconverging optimizations. We then discard this instance if the surface error is above an acceptance threshold, avoiding misclassification errors. and if not, we combine the matrix M with the denormalization transformation to obtain the final instantiation matrix. To evaluate the proposed framework, we used a CAD model composed by 1800 geometries labeled in 16 base geometry types. The final optimized model has a good quality, having a small mean surface error and standard deviation. When compared the memory reduction with the Ibsen and Seles work, we were able to obtain a very close result to theirs. However, when shuffling the dataset, since the triangle meshes can have different triangulations due to different modeling techniques, we still maintain the same memory reduction, while the Ibsen and Seles work perform poorly, since they are very topology dependent. We also perform a series of experiments using different methods for optimization, with ICP, using our loops and not, and also the other optimizer with chamfer distance. In this table, we can see that we were able to outperform the average time of all other methodologies, and although using a more relaxed acceptance threshold, the memory reduction were very close. When using a more rigorous one, we still maintain a good memory reduction, while the others start to perform poorly. Finally, we use the same base geometry types to optimize a different model, and the result was not as good as the previous one, due to the lack of similarities from the base geometry types. The misclassifications were pruned by the acceptance error. We presented the Shape Instance registration framework, which were able to obtain a significant memory reduction by relying on PointNet++ and Add Optimizer, overcoming major drawbacks from previous works by relying on point clouds. As future work, we intend to investigate the use of clustering techniques to avoid the necessity of previous known knowledge about the model, and apply the framework in other scenarios.
Yes. So thanks, Lucas, for
Thank
the
you.
presentation. So this is a very, very nice technique for saving, memory while storing very precise CAD representations. And my first question is, do you foresee any problems in extending this to also handle not just those primitives that you showed, but also more complex CAD parts such as pumps, valves, etc.?
Uh, at first, we don't see any problems. We designed the algorithm to handle any type of generic meshes. It's just a coincidence that these base geometries were like some kind of parametric geometries, because this was the ones that were labeled in the dataset. So we intend to exactly future work use some unsupervised methods to test this framework with other greater range of generic meshes.
Okay. Just as a follow-up on the previous question, I mean, is it necessary to have a minimum number of, say, primitives, polygons or so, in order to make this technique advantageous if you move to more complex, say, CAD parts, as I mentioned? For instance, you need, at least 10% of the polygons in this representation, those more complex parts, before it becomes advantageous. Otherwise, it would be, you'd be wasting more memory on doing this.
This is a very interesting question. At first, I don't think we can actually have some kind of downside to doing so, because when we used for example, if we have two meshes that are similar to each other, and you can use an affine transformation between them to transform each other. The matrix is very compact to transform and instantiate some object from another. And it's more likely that the mesh is more discretized than the compact representation of the matrix, since when you optimize the model, you have just one triangle mesh and multiple affine transformation to instantiate the model. In terms of rendering performance, we actually did not test such a scenario where it may be better to maintain the original meshes to obtain better rendering performance.
Okay, so we have a question from Joaquim Bento. Is your method affected by the mesh density?
Assuming that the mesh density you mean is the point cloud density, yes, indeed, we during the optimization procedure we have an outer loop that we increase the density along with during the optimization. All right, we start with a not so dense point cloud, and then we increase this density during the optimization to obtain a better result, a more fine result at the end. And I was kind of doubt of what they mean by the mesh density, but if the mesh density will also mean by the number of vertices or triangles, it's not that really affects the optimization and the classification problem, since during the point cloud sampling, the probability of a point relying on a triangle depends on the triangle area. So it's proportional to the triangle area. So we can obtain an uniform point cloud sampled on the mesh.
Okay, and so talking about point clouds, how could you extend the proposed framework to handle 3D point clouds representations? Meaning, instead of starting from a polygonal model, you had a scanned version of this environment.
I think it's in this case should be some kind of perhaps small tweaks on some parameters, but it should be very plug and play scenario, such as we have the original meshes, right? And we sample point clouds because all the process relies on those point clouds. And then we retrieve the mesh instantiated in the model. So we also propose this feature work while using this technique in other scenarios, use some scanned real point cloud data that can be used in some scenarios such as built scenarios where the engineering facility have some maintenance or changes
Have you done this? You used
no.
Yeah, because in an actual scanning environment, you have to consider that the density of the points vary with the distance from the scanner. There are occlusions, so I mean the data is not. There is a lot of noise, so the data is not as clean as the ones you use. But it's great work, very nice work. Unfortunately, we have to stop here because the time for our session is almost up. So thank you again, Lucas, for the answers. And so for all of you in the audience, you can continue the conversation with the authors on the session's Discord channel. So please do so. And I would also like to remind you for our upcoming event. is the keynote, our first keynote of the conference by Professor Luis Gustavo Nonato. It's going to be at 11 o'clock, so stay tuned. The title of his presentation is going to be From Geometry Processing to Spatial Temporal Data Analysis and Visualization, a Historical View. So please stay with us and attend this nice talk by Gustavo Nonato. And before closing the session, I would like to thank again all the authors from the session and all of you also who attended it and also contributed with your questions. So thank you very much. And this concludes the session.